Up until now, the special quadrilaterals we have been doing have been parallelograms. Section 6.6 covers trapezoids and kites, two special quadrilaterals which are not parallelograms. A trapezoid is a quadrilateral with exactly one pair of parallel sides. It looks like the shape I have drawn. Most of you have probably seen one before. Note the definition specifically says exactly one pair of parallel sides, so it is not a parallelogram, and does not have the properties of a parallelogram. So opposite sides aren't congruent, diagonals don't bisect each other, all of that stuff. When we covered isosceles triangle anatomy, we had one base and two legs. The congruent sides were the legs. The leftover side was the base. The sides of a trapezoid are named the same thing, legs and bases. The difference being that in a trapezoid we have two bases instead of one. The two parallel sides are the bases, the other two sides are the legs. Some students want to force it and make sure the bases are down, but it doesn't work that way. The parallel sides are always the bases, no matter how the trapezoid is oriented. There are four angles in a trapezoid, and all of them are next to a base, so all four of them are base angles. That is so not helpful. They are all named the same thing. We should just call them interior angles at that point. In any case, the thing you do need to know is that the base angles come in two pairs. Each base has its own pair of base angles. That's all for trapezoid anatomy. The trapezoid I have largely been working with up till now happens to be an isosceles trapezoid. Two of the sides were congruent. Seems pretty straightforward, right? But how about this? Does this count as an isosceles trapezoid? What do you think? This one is often a bit harder for students. What's your guess? The answer is that this does not count. This is not an isosceles trapezoid. An isosceles trapezoid is a trapezoid with the legs that are congruent. The two congruent sides must be the legs, not just any two sides. When we had isosceles triangles, we showed that each of them had an axis of symmetry. Isosceles triangles are lovely symmetric shapes. We can do the same thing with isosceles trapezoids. Each isosceles trapezoid also has an axis of symmetry. Isosceles trapezoids, just like isosceles triangles, are symmetric shapes. There are two theorems that involve these isosceles trapezoids. The first theorem you could figure out if you knew that these trapezoids are symmetric. Let's look at it. In an isosceles trapezoid, each pair of base angles is congruent. Since isosceles trapezoids are symmetric, that should make sense. It's handy that they clearly look congruent too. This is the second theorem involving isosceles trapezoids. In an isosceles trapezoid, the diagonals are congruent. Once again, the symmetry comes into play here. In the case of this picture, this theorem lets me definitively say line segment AC is congruent to line segment BD. That's all there really is to say about this theorem. It's hopefully pretty self-explanatory. Here's a slide from way back in section 5.1. Forever ago, right? In that section, we showed you what midsegments of triangles were. Do you remember what a midsegment is? Do you remember seeing this slide before? Now we are dealing with the midsegment of a trapezoid. The midsegment of a trapezoid is the segment that joins the midpoints of the legs. Very similar to the midsegment of a triangle, right? One thing to note. It very plainly says that it is the midpoint of the legs. It won't work on just any two midpoints. It must be the midpoints of the legs. It doesn't have to be an isosceles trapezoid like the one here either. Midsegments exist for both trapezoids and isosceles trapezoids. For the record, some books will call a midsegment the median of a trapezoid. And just to confuse things even further, some other books will call it the midline of the trapezoid. They all refer to the same thing. Of the three choices, midsegment is nice because it mirrors the midsegment of the triangle, which is so similar to it. If we decided to call it a median instead, students have to keep track of the differences between a median of a triangle and a median of a trapezoid, which are two very different things. Since that doesn't work as nicely, I will always be referring to it as a midsegment, but I wanted you to know that there are other possible names for it. This is the triangle midsegment theorem. It's one of the few theorems where there are multiple conclusions. The first conclusion is that the midsegment is parallel to the bases. This is just like the midsegment of a triangle, which was also parallel to the third side. The second conclusion of the theorem says that the length of the midsegment is half the sum of the lengths of the bases. That's fine and all, but another way to say it is that the length of the midsegment is equal to the average of the bases. Students usually prefer it that way. Use whichever makes more sense to you. Half the sum of the lengths of the bases, or average of the bases. Ready to go back in time again? This was the slide that talked about the triangle midsegment theorem. Notice how similar all of that is. Both of them have two conclusions. One of them is talking about being parallel. The second one is a calculation. In this situation, you can think about it like 10 is the average of 20 and 0. So if you think about it like that, the midsegment of a triangle and the midsegment of a trapezoid are just about identical. Back to the current lesson. On to kites. A kite is a quadrilateral with two pairs of congruent sides. Parallelograms also have two pairs of congruent sides. However, a kite is not a parallelogram. How is that possible? Do you know? We know that having opposite sides congruent is one way to prove that a quadrilateral is a parallelogram, or at least you should know that. Using indirect reasoning, we can rule out that the opposite sides are congruent. So if it isn't the opposite sides that are congruent, how about consecutive sides that are congruent? Officially, the definition says a kite is a quadrilateral with two pairs of consecutive sides congruent and no opposite sides congruent. It kind of ends up looking like, well, a kite. Not that kids play with those much anymore these days. I could go on a tangent and go into kite flying competitions, which are actually pretty brutal and fascinating, but sadly, I will just stick to geometry for now. You probably didn't even know that there were kite flying competitions and championships, did you? The special properties of both rhombuses and rectangles had to do with diagonals. The same is true for kites. Its special property also has to do with the diagonals. Here are a lot of different kites with their diagonals drawn in. Do you notice anything in particular about those diagonals? They clearly don't bisect each other. That would make them parallelograms anyways. Anything else of note? Did you figure it out? If a quadrilateral is a kite, then its diagonals are perpendicular. Nothing much else to say about it. They should definitely have looked perpendicular because, well, they are. Now the book doesn't go into this, but since we have talked about symmetry, a kite is also a symmetric shape. This is some vocabulary you don't need to know, but the angles formed by pairs of congruent sides are vertex angles, and the other two angles are non-vertex angles. Like I said, you don't really need to know the terms vertex angle and non-vertex angle. But the axis of symmetry is the diagonal which connects the vertices of the vertex angles of a kite. The other diagonal is nothing special. Okay, sure. Everyone is special in their own way, even you. I bring up this whole axis of symmetry thing, even though the book doesn't, because it is incredibly useful in helping you fill in the pieces of the kite. We already knew that the sides were congruent. We already knew these sides are congruent, due to it being a kite and all. We also know that the diagonals are perpendicular. None of that is new. However, if you know that this dashed purple diagonal is an axis of symmetry, then you know that each piece on one side has a matching part on the other side. The one diagonal is bisected. All of the angles on one side of the axis of symmetry have a matching partner on the other side of the axis of symmetry. Knowing that will help you fill in the kite problems much quicker. Very handy. I'm surprised the book didn't cover that.